One thing that Gary and others are confusing is this idea of statistical error analysis with what's going on in quantum mechanics. Okay, now with the statistical error analysis, that applies to classical mechanics and quantum mechanics both. And to things like, for example, how well can you know the mass of an electron? We know it pretty well. Okay, but when we measure it, we will get, plus or minus some amount of error. Okay, so we propagate this error through our calculations. We know how when we take one measurement and another and they have different errors, we know how to combine the measurements, combine the errors, and we can keep track of that. Okay, but in the two-slit experiment, such a thing as that just changes how far the bands are in the interference pattern. When you see the pattern that results in from the two-slit experiment, an interference pattern, it's bright and dark bands. Okay, and the mass of the electron or the particle, these kinds of measurements would change how far apart those bands are. Okay, but that's not what we see in the two-slit experiment. By having two slits, we're not dealing with an error propagation problem. We're testing whether this probability wave is a real thing, because waves would hit both slits at once, like a wave would come up, and part of the wave would go through in each of the slits, and that makes like a new wave source. Whereas a particle doesn't work like that. By having two slits, we don't see the bands go closer or further apart or any of the parameters that we've calculated, with only a limited degree of accuracy change. No, we see the pattern change, not just some feature of the pattern, but the actual nature of the pattern changes from a one slit diffraction pattern into a two slit diffraction pattern. Okay, so the pattern is different in a gross way, not in some fine tuning way within the error of our statistical error analysis, but just totally different pattern. You know, so it's totally orthogonal. The issue of randomness in the probability waves is different from a handling statistical error with based on the fact that our measurements are not accurate enough. It's entirely different. The quantum pattern arises even if you know exactly the mass of the electron, you know its exact particle wave duality. It has to do with the fact that it does have a wave nature in addition to the particle nature. And as Gary, as you pointed out, waves have mediums, and there's energy in mediums, and it's an interaction of these things. And that's the point. There's some sort of a medium, a probability medium, or a medium that corresponds 1-to-1 with probability, that is the medium upon which these electrons really are disturbances. They really are energy flowing across this probability medium. And the reason I say really is because the fact that the particle as a wave manages to go through both slits, interfere with itself, even though by the time it hits the screen, it'll basically regain or retain or have a particle nature when it hits the screen. That's the weird thing. And it's somewhat separate, but of course it's related to this weirdness of there being a wave particle duality. We just accept that. Gary's just like, well, it makes sense that light is. It doesn't make sense that light is a particle. I mean, we know light is literally a wave. It's a wave in the electromagnetic field. That, it really is a wave. That's not just a metaphor. It really acts like a wave. Yet it also acts like a particle, making one speck at a time on photographic paper. So that weirdness is almost a whole other subject of how that could be, and why intuitively you want to accept it for light but not for electrons and that sort of thing. Whole other subject. The subject of the two slit experiment is that in order for it to see this interference, it has to interfere with something, and we're only firing one particle at a time, so it's interfering with itself. And no, it's not going back in time and interfering with particles at some other random location in space. That does not make a lot of sense. And what the two slit experiment definitely shows us is that something weird's going on, right? If it's what the quantum uh, physicists say, or if it's what Gary says, something very weird is going on. Some time travel, or multiple universes, or there really is randomness in the universe. I mean, that latter one seems a lot easier to accept than the other, but whatever. They're all weird in the sense that we know, even though we don't know full explanation, we know there is no classical explanation because classical rules are violated in these experiments. Classical rules won't explain them. We know that it's weird enough. We need something beyond the classical rules. So insofar as you have a desire for the classical rules of physics to apply, you lose. You know, they don't. Insofar as you want to come up with your own weird theory, well, you have as much right as any physicist to attempt that. But you really will need to understand what's known about the experiment in quantum physics and other quantum physics experiments and phenomena, and what the real proof of the uncertainty principle is, and stuff to understand that no, it's not a problem, it's just the tweezers being too big. Okay, there's more to it than that according to the theory, which you can overturn those theories, you can overturn Heisenberg if you want, but it's not going to be by ignoring the facts that we have in experiments. It'll be by understanding them really well. So anyway,